This is the Church of San Cristobal in Cusco, Peru. All of the old churches in Cusco are built on ancient Inca ceremonial sites.
In 1950, an earthquake shattered colonial churches in Cusco, sending stone and plaster tumbling into the streets. But just meters away, an ancient wall of 200-ton stones shifted, flexed, and remained intact. Engineers would later measure the movement. What they found wasn't brute strength. It was something far stranger: stone, behaving like memory. The paradox, in plain sight. At first glance, the massive stone walls scattered across Cusco and the Peruvian highlands appear like ruins from a lost world, ancient, immovable, enduring. But they are not just relics of strength. They are survivors of motion. These walls, built from massive irregular stones weighing as much as commercial airplanes, have withstood centuries of devastating earthquakes, not by resisting movement, but by yielding to it in precise, intentional ways. During major quakes in 1950 and again in 1986, Spanish colonial buildings cracked, buckled, and fell. The Inca walls, by contrast, flexed. The stones shifted slightly, almost imperceptibly, then returned to their resting positions. There was no collapse, no need for repair, just stone that behaved more like a jointed organism than a rigid structure. This contrast, failure beside flexibility, should not be possible. By the rules of traditional engineering, stone is brittle, unforgiving, and prone to fracture. The Inca walls defy this expectation, not once or twice, but again and again. And yet, for centuries, the real secret was not their mass nor their age. It was a system hidden in the geometry, an architectural paradox hiding in plain sight, where motion is not the enemy of survival, but its very mechanism. Precision that should not exist. Everywhere these walls appear, Cusco, Ollantaytambo, Sacsayhuaman, the pattern repeats. Massive stones, each with wildly irregular shapes, slot into one another like pieces of a three-dimensional jigsaw puzzle carved by an unseen hand. No two stones are alike. Some have 20 or more distinct faces, each one carefully angled and curved to match its neighbors. And the gaps between them, often less than half a millimeter, tight enough that not even a razor blade can slide through. But this precision raises an uncomfortable question. Why? In modern construction, such meticulous shaping would be unnecessary, even wasteful. A stable wall can be built with far less exactitude. Mortar fills gaps. Gravity does the rest. Yet these walls were built without mortar, and with far greater care than seems structurally required. The stones curve inward, sometimes outward, fitting together in ways that appear organic, almost biological. This level of craftsmanship comes at a cost, not just effort, but time. Thousands of man-hours per block, according to experimental reconstructions. And the more complex the shape, the more the time compounds. So, why do it? Why pursue geometric perfection with 100-ton blocks that didn't need it? That is the riddle. These walls are too precise to be random, too advanced to be accidental, and too impractical to be explained away as aesthetic flourish. Something else is happening beneath the surface, some principle not of artistry, but of engineering. And it isn't until we try to replicate it that we start to understand just how far the problem stretches. Experimental archaeology reaches its limits. In the 1990s, architectural historian Jean-Pierre Protzin set out to replicate the Inca building method with period-appropriate tools. Using granite river stones as hammers, he and his team pecked and abraded limestone blocks into shape, slowly, laboriously, and with genuine respect for the builders he was trying to emulate. And while the technique worked in principle, it soon revealed a critical flaw. His test blocks were small, rectangular, and flat-faced. Nothing like the complex puzzle-like stones of Sacsayhuaman. Even with the most favorable materials, it took days to shape a single flat surface, and fitting multiple stones together required endless corrections. When scaled to blocks weighing 100 tons or more, the process broke down entirely. The idea of lifting, testing, reshaping, and resetting such a stone repeatedly became a logistical absurdity. Modern engineers would use computer simulations, laser scanners, and digital pre-visualization to avoid these problems. But the Inca, working with no written language and no known measuring tools, would have had to work by feel and by eye. That seems implausible, not impossible, but mathematically implausible at this scale, and with this consistency. And so, despite the best efforts of archaeology, replication stops at the threshold of complexity. The moment the stones begin to interlock on multiple axes, theory collapses into speculation. What remains is the understanding that these walls could be imagined today, but building them, especially without modern equipment, lies far outside the bounds of traditional experimental archaeology. The missing piece. There is one assumption hidden in nearly every reconstruction, and if it's wrong, the entire problem changes. What if these walls weren't fully shaped before being placed, but shaped while being placed? Not lifted, tested, removed, and reset repeatedly, but assembled under load, one stone at a time, with partial weight already bearing down as adjustments were made. This is a subtle shift, but a decisive one. If stones were seated gradually, levered, rotated, nudged into position, and then worked while under pressure, their contact faces would not reflect idealized geometry, but real stress-aligned contact. Curves would emerge naturally, microgaps would vanish. Precision would no longer need to be measured, it would be enforced by gravity itself. This explains why contact points flow rather than meet at hard angles. It reframes the absence of visible debris. The shaping was not purely subtractive, but interactive, evolving as each stone locked into a growing, load-tested matrix. The system wasn't just complex, it was adaptive in real time. And it's not just theoretical. In 2008, researchers at the University of Tokyo constructed 2 full-scale test walls, one from concrete, one modeled on Inca-style interlocking stone. Subjected to simulated seismic waves, the concrete wall cracked. The stone wall flexed. It survived. Their analysis labeled it a nonlinear dynamic absorber, capable of dissipating energy through geometry alone. These aren't just ancient stones. They are engineered joints, and their strength isn't only in how they stand, but in how they were assembled, not despite flexibility, but because of it. The Flex system revealed. In 2005, researchers from the Pontifical Catholic University of Peru used laser scanners to monitor Inca walls during seismic events. What they found defied expectations. As tremors rolled through Cusco, individual stones shifted, just millimeters. They pivoted, they lifted, they settled back into place. This wasn't symbolic movement, it was mechanical choreography, stones moving with the earth. This behavior should be impossible for dry stone structures. By conventional logic, stones without mortar should separate under vibration. But here, the opposite happens. The more the earth moves, the tighter the system locks. Overlapping curves and intersecting faces press against one another like gears in motion. Movement isn't tolerated, it's required. In engineering, this is called dynamic interlock. But here, it behaves almost biologically. Self-adjusting, pressure-absorbing, repeatable. Modern seismic systems use steel springs and flexible pads to achieve similar results. These walls do it without a single modern material. In 2019, Japanese researchers ran simulations on digital models of the Sacsayhuaman walls. Their conclusion was clear. The geometry is mathematically optimized for energy dissipation, not by coincidence, by design. And that design makes sense only if the Flex system was created during construction, not imposed afterward. Rethinking time and builders. For decades, archaeologists have credited the Inca Empire, flourishing between 1400 and 1530 Common Era, with the construction of these walls. But multiple clues suggest a deeper, more layered story. Spanish chroniclers noted that the Inca themselves seemed awestruck by some structures. They could replicate simpler forms, but not the intricately interlocked foundations of sites like Sacsayhuaman. Even today, the difference is visible. Lower courses show seamless, complex geometry. Higher additions show mortar, cruder joints, irregular stone, signs not of progress, but loss. Recent ground-penetrating radar surveys have revealed older foundations beneath several sites. suggesting multiple construction phases spanning centuries. Some researchers, like Arthur Poznansky, argued that the most sophisticated stonework may predate the Inca by far more than history allows. While controversial, these ideas point to one thing. If the logic behind the flex system was once understood, it may not have been preserved. The walls we see today may be remnants, not just of stone, but of a method. These stones were never just a wall. They were a response to earthquakes, to time, to complexity itself, built to move with the world, not defy it. If you want to understand how ancient systems outlast modern ones, explore the next chapter here. Or better yet, subscribe and come rethink the past with us.